Okay, basic concept on the structural reliability is concerned. The lecture notes I gave you last Monday morning or over the weekend. That's really basic concept on there. But next step is computational. How to compute that? It's very easy to give you the formulation for the structural reliability problem. But question is how to compute that. That's the next step. Before the next step, I want to cover few chapters of this book. Higyu has two sets of copy. Okay, you can share together. This is a safety factor and reliability. And Professor Isaac Elishikov is a good friend of mine. I know him something like 20 years. And he was born in Georgia. That was a part of Russia before. And he is a student of Professor Bolotin, a Russian scholar, very well known in the reliability area. And he returned to his country, Israel, some 30 years ago. Then he stayed in Haifa Institute of Technology, but he eventually came to U.S. and he's right now in Florida still teaching out there. And I want to bring him here sometime, I hope next year, maybe a month, or I have to talk to him. I haven't talked to him. Very nice gentleman. And some short course, something like a few days short course we can really do for the students. Exposure, what other peoples are doing. That's what I want to do in structural reliability area. And that book, I'm going to cover few chapters because you will hear when you go out to the industry or a research lab, you will eventually involve in the design, not only analysis, but the design. Design, as I keep saying, is not the iteration process of analysis. It's a whole thing. You start from the beginning with a totally different idea. So yesterday we have a visitor from Jeonpyeongdan, the Navy kind of the lab here in Gyeongdae, and he gave a seminar. You were there yesterday at 4:30 in Gigedong, the seminar room, and he is one-star admiral, the Naval Academy graduate. I really talked to them in the dinner time. I want to really see. He keeps saying KAIST students are great. Of course, it's great. And I said. Then he said, young people in Korea is great. The question is how we can drive them out and they can get the Nobel Prize. So before getting into that mode, I said, I want to really see the KAIST students think differently. Like Steve Jobs, in a recent death. I never met him before, but whenever I see him, in the news and all that, gosh, he is different. But different means he was a kind of the radical person, very radical person. Radical doesn't mean in the bad sense, bad guy or good guy. He's something different from others. And the initial thought I had before when I came in here 2 years ago, how we can drive the KAIST, such a smart brain, differently from other. And a lot of thought arises. We have a discussion among the faculty and so on. But it should come from your brain, not from the old people. Old people means it's really traditional, right? But the mind to change the world is from you, from blank. That's what I see it. Innovation, that's what another word. Professor Berrigan is teaching some innovation design. Okay, so it's clear. The Friday I want to see your presentation. I'm going to really read thoroughly this afternoon. After this class, I'm going to spend to read all the 4 project reports. Okay. Okay, today there's a few lectures I want to do. Few different cases here, for structure reliability situations. And this means still I used this before, S or P, resistance and loading, P, or resisting stresses, R, or resistant strength, R, and S is like applied stresses, the actual stresses, you can think of that. And in the design process, you always face how reliable this component is, how reliable this system is. Then what kind of the safety factor do I have to use? In the design process, to get the final innovative configuration, of course, in the structure mechanics, you have to apply the design load to the system. Design load to the system. So how the safety factor or factor of safety concept applies in the design process. I'm insisting you multiply the safety factor to the actual stresses or actual loading, not the reducing the strength, resisting strength. Because, for example, for the buckling problem, loading and resistance relation is, or loading or stress relation, buckling stresses, is nonlinear. So for the safety reason, you will apply the safety factor to the actual loading to get the design loading. Then basic questions, as Elishikov clearly indicated, that's the main reason I picked this up. I'm going to cover a few chapters on this. How does safety factor relate to reliability, structural reliability? How does it relate? Safety factor. You heard about the safety factor, right? How did you use it? How did you make a connection to or translate into the reliability of the system? That's the question. So few cases we're gonna talk. I'm gonna say actual stress. Don't be confused, stress, actual stress. If you have a load as a pound, for example, then you can translate into the stresses, apply the stresses or actual stresses. So actual stress could be random. What does it mean, random? You can cast into the or assign the statistical property, like what's the mean stresses, mean actual stresses. Then what's the dispersion of actual stress cast into the variance of the loading or stresses. So it's a random situation. And then resisting strengths. I can use the stress, but use the strengths. Resisting strengths can be, of course, random. But first, let's look into what's happening if it's a deterministic. Because the quality control in POSCO, producing the steel, quality is so good. What does it mean quality is so good? In terms of the standard deviation of yield stress or ultimate tensile stress of the steel or aluminum is so small, it's almost deterministic. So as a user or builder, we can assume the yield stress is deterministic. What does it mean deterministic? If you cast into the probabilistic sense, deterministic is one value, period. There is no dispersion. Just one value, yield stress, 36 kpsi, that is it. Okay? Then what happened? How simple is that? Another situation could be actual stress could be deterministic. Actual stress means actual loading. There is not much variation. It's very little standard deviation or variance. And it's really coming from the gear mashing in the machinery system, then I want to just use the one typical value for the loading, perfectly fine. You don't have to cast into the probabilistic model, then you don't have to really get all the different experimental data. One value, deterministic value, then actual stress is very much simplified, then you can compute without any big hassle. And resisting strengths random. You sometimes you don't have any other choice but using that material, which is really not great material, but you can put the design into it. Then you have to make sure that system is safe, is reliable. You have to meet like a 10 to the minus 6 power for the probability of the failure. Almost the perfect situation. Can we do it? Well, you have to perform the computation. What happens if it's in this situation? And of course, 3 is we treat all for random, for both random. That's why we treat that as random to compute the probability of the failure. That's what's happening. And over here, when we do this, of course, we will discuss how to handle deterministic and for the random, then you have to bring the probability model. Probability model, we have enough. We have 6 in previous section, but we'll bring a little bit more, like a uniform distribution model. Very straightforward. So we're going to bring back such a model and use it. Then get the feel of it. I'm insisting to you, get the feel of it. Start from the equation, end with the equation, no feel, then that's a disaster. As an engineer, we are rather be engineer after you graduate with a master's degree or PhD, rather than the physics scientist, then you came to the wrong place. Especially ocean systems engineering is more. You should be fully really engineer. That's amazing. So this area, to get the feel out of it, what happens if you use a log normal distribution rather than the normal distribution for this particular design? Is it doable? Is it reliable? Is it gonna work out well? Is it going to represent the actual real data? I want you to have a sense before you really get into solve the problem. Right now you could say, I have to solve the problem. Then I can get you. You wait until I solve. Of course that's the right answer. But at the time, at the point you graduate, you should have a feel of it first. Feel of it. That's what the experience counts. That's what your thinking will provide. Such a pre-sense of what's happening. Of course, when you do PhD, doctoral degree, of course you have to really going into the bush. There is no path clearly showing, but after for a while you should be able to see the path that you want to really pursue, you want to go. Oh, my advisor, my professor will lead in front of me, then I'll just follow. Then you are the technician. You are the technician, no more than that. But for master's degree, I agree. The thesis work doesn't have to be the really absolutely new approach or new theory whatsoever. Or could it be sometimes? Sometimes some students really investigate, which is really quite new, but usually that doesn't have to be for master's degree. So this is the model. This is the model we're gonna really check out and get a sense out of it, and we will evaluate. And as a part, I'll assign some homework, design-oriented as much as I can, not the analysis. Even the day before I assigned a simple homework, I give you the answer. Of course you will derive to get the result. Could it be slightly different? Could it be different? But you will do that. But now, next step is my question. Okay, that's what that more design-oriented sort of things. Okay, first of all, now before I getting into all this, safety factor. If you look at the vendor's spec or design spec or ship building manual, you will see the desired safety factor. Safety factor is not just came from somebody, some designer's mind. The background is reliability. Safety factor, reliability is supposed to have one-to-one relations. Then what sort of the safety factor the people is using it? Some people are saying, I have no idea. All they know is a fuzzy factor. They call fuzzy factor. Everything's all uncertain. Then we have to multiply some factor, which is called the fuzzy factor, which is not quite desirable. Strict sense, the safety factor should be translated into the structural reliability in this course, or structural reliability has to translate to the safety factor. then what's the safety factor? So, of course, people define differently, depend on their field, but mu is something like, in the general sense, R divided by, I'm going to just write here, safety factor, as a S. This is like a resistance, and this is a loading. So how much cushion do we have? That's a typical definition of the safety factor. And in the conservative sense, people defines, well, I really want to set, this is looks like a M, this is a mu. What's a mu in our notation? It's mean value, that's what we and mu S, earlier thought, then they feel, wow, this is mu R, that's a mean or expected value of the resistance. Well, let's play safe. So I wanna take away maybe 2 sigma. This is just the example, okay? Example here. 2 sigma R. So here, when you deal with the probability model, let's call this, if it's normal, right here is mu R. Well, I want to really reduce the 2 sigma R, then I'm going to set that point as the design resistance, okay, like this, for example, okay. But for the loading, mean loading or mean actual stress or mean applied stress, let's jack up a little bit. That's what the people classically, the designer uses such a division as safety factor. I need that much cushion, otherwise it's too much risk. If the structure system collapses, then I'll be out. Play safe. But people saying, no, this is not the way to do. As time goes along, then what they defined as the structure reliability advances, then one safety factor. Well, let's play a strict sense. It's too much hassle, too much fuzzy factor, and safety factor. Let's define the probabilistic sense. Let's do as I'll introduce a new kind of the variable. It's all same. I'm gonna follow the Elishikov terminology. Then once you start reading the few chapters which I'm giving a lecture, then you can easily adopt. Okay, you can easily adopt. So that's what I have decided here. You know the over here. You know the E, which is expected value. Okay, And expected value, if it's x, how do you get that? So integration minus infinity to infinity, x times fx, first order of moment. So again over here, we spend about a week or 2 weeks to look at the probabilistic model. We needed that for continuous model. So here, and we are going to use in next 2 weeks, or we'll see how it's gonna go. Sigma, I don't know why he used it, but we'll use the same notation to easiness to understand the terminology. It's random variable. Okay, when I use a sigma, it's a random variable. And if I use like this, sigma, say lowercase of the sigma, this is like a specific value. So it's given or specific value of the sigma. For example, F sigma and sigma, specific value among the random variable. So here, then here is sigma r. What does it mean here? Random variable r, the resisting stresses. Here, I'll just use stresses. It could be the loading, okay, as a pound, but stress is like a PSI. Here in metric system, what do you have? Pascal, right? Megapascal. So it's resisting resisting random variable, resisting strengths. Today's not Monday, it's Wednesday. Resisting random variable for resisting stress. Makes sense. This is easy. And hey, you better change this guy. Is supposed to be what? Sigma S is random variable for actual stress. Resisting stress, or really we use resisting strength, is all same thing. Okay, nothing to confuse, right? That's what the notation he used, and it's easy. So this is called central safety factor. Central safety factor. And this is the most popular. Okay. This is the most popular, and this is what I'm going to use it, of course. to translate into the reliability, or the translate reliability to safety factor is really, we're going to talk the central safety factor. If you usually, or if I usually say safety factor, this is the one I'm talking, central safety factor. And all other types you have, let's say N2 could be E to the another type, okay? Take the expected value of sigma r over sigma s, and other is like N3 said, well, I want to make it something different, and I'm going to take the whole thing as this. Okay. But central safety factor is what I usually do. Okay. Again, always back to the definition. Probability of failure. Probability of survival, or this is equal to the reliability, structural reliability of the system. Probability of the failure is, of course, 1 minus r. So if you compute the one, you can compute the other one. So the reliability r is equal to probability, such that easiest way to remember is yield is always higher, yield stress is higher than actual stress. So cast into probabilistic concept is sigma r is greater than sigma s. So using this notation, sigma r is greater than sigma s. Very easy way to remember. And when you're dealing with the multiple, the multi-dimensional concept is identical. So this is, of course, is very clear, but probability of the failure directly cast the probability model, and this is equal to sigma r is less than equal. We want to put the equal at the one side. For the multidimensional, that's a limit state surface. Okay, limit state, include the limit state surface means it's right there. It's a borderline. And sigma s. Okay. Whole thing falls in this category. So in this case, sigma r is the resistance treat as a random variable, I'm going to say that this is a deterministic. And just a reminder, we're going to deal, this is random. Then I'm going to say that as a first simple model for the random variable, of course, I'm going to say the model, probability model, is uniform model. What does it mean, uniform model? Uniform probability model. Any sense? Uniform. So if I draw, this is S, this is Fs, of course I can say S, uniform, start stress, let's say lower limit, and this could be the upper limit. Lower limit could be start from the 0. Sigma u could be higher, lower, and uniform. That's what the step function is. And this value and area under should be what? Yes, sir. 1. Total probability. Just the integration of the whole probability density function is 1. So area is 1, then what would be the height of the density function? 1 over sigma u minus sigma L. That's called the uniform probability density function. So this is a typical of uniform probability density function. So simple, I'm gonna draw the probability distribution function or cumulative distribution function. So if I just draw this red, this is FS, cumulative distribution function for actual stress. If I do that, you expect when sigma u at the point sigma u is there, the probability distribution function, what's the value you expect? 1. So this is a 1. After 1, what do you expect? Still 1. Right? When you're married, after the honeymoon, still you're married. 10 years after, you're married. 40 years after, you're still married. But not nowadays. They just to quit. That's a bad. Arlene, right? That's bad. So it's a straight line, right? After that, right? Make sense? That should be it. And when stress is lower than sigma L, what's the cumulative distribution function value? 0. So it's a 0. All the way 0. then after that is a uniform. It should be straight up, right? Straight up. Then what would it be? Simply FS model. It's simply start sigma u minus sigma L, and the lower value is sigma L, and any value is sigma. I'm going to say I use S here by accident. I'm going to say here. When S is sigma L, replace S by sigma L, then its numerator is 0. It's 0. When S is sigma U, what happened? Sigma U minus sigma L, up and down, then that's a 1. So this is a typical model. Usually for the, in this case, I can say X is, sigma is not 0. What's the effective, effective region is S equal to sigma L to S is up to sigma U. So in this case, S is between. That's effective region. All other places equal to 0. And this is equal to 0 when S is equal to less than 0, and this is equal to 1 when S is equal to greater equal to I'm sorry, this is sigma L, and this is a sigma U. I can say this is, this is okay. So this is a typical uniform distribution, but not used really this model for time to failure. Not good model. Time to failure model is typically what model? Jungan. Yes. What model do you use for time to failure? Usually exponential type model, which is a family of extremal distribution model, okay, part of it. So it belongs to exponential or Weibull distribution, all belong to that type of a probability model. And now we are in business, so random is random load stresses that uniform, and using something like stresses, and this is Fs, okay? Then in this case it's a straight line, but some other type of the model, you know, you could have many different kind of probability model. And for the resistance is concerned, it's a deterministic. That's what we are looking for in this case. Deterministic, which means one value. S sigma y period yield stresses. Then this is all it cares. on that. I think we'll stop here, then we can formulate. Once you do the formulation for ones and get the solution, then next to type a few different probability model, I'm going to use it. Then I want you to get the feel of it. Then we'll go into the another case, okay? So I'll see you Friday morning, and pick up your term project before 5 o'clock from Higyu. Okay, we'll see you then.